right, so we're going to use 8, negative 9, and negative 3, 2. You can draw those, right? We'll just draw them in position form. That means they're at the origin. So 8, negative 9, and negative 3, 2. This was U from yesterday's lesson. This was V from yesterday's lesson. And now we would like to notice something. It says, notice, the vectors U and V span a parallelogram when they're placed tail to tail. So I put them tail to tail. Can you sort of imagine a parallelogram here? It looks like this. This fourth point would be at 5, negative 7. Okay, so it's kind of like a parallelogram. Go ahead and plot. The easy way to do it is just plot the point 5, negative 7 for me real quick on there. Just plot it. And then you'll see what I mean. You can use your straight edge and form a real nice parallelogram there. Take a moment to do that. Plot 5, negative 7, you'll see what I mean. Okay, now you'll notice if you draw the diagonal, the one that comes from the tails of U and V, if you just draw this diagonal here, and you put a head at the bottom there, this vector, since it starts at the origin and it goes 5 right and 7 down, this green vector is the vector 5, negative 7. It is the vector 5, negative 7, you see. So I just drew one more thing. Go and add it to your picture. You're going to connect from the origin to the point 5, negative 7. And this is what we call the diagonal of the parallelogram. Right? The diagonal of the parallelogram. 5, negative 7 is the vector that connects the origin to the opposite corner. Okay, now, notice, when you add the vectors U and V together, what do you get? Obviously, by adding, I mean just add the x's and add the y's separately. So what happens if you add the x's and y's? 5, negative 7. Interesting. So our first, I guess, investigation seems to be about adding vectors. It seems like, this isn't a proof, but it seems like when you add vectors, you can do it both algebraically, just add the numbers, or geometrically. You can either add the x's and y's or draw a parallelogram and then connect the diagonal. Either way, you get the vector 5, negative 7. It seems like this might be a general truth, something we could use in the future. Okay? So what would our conjecture be? Something about a parallelogram's diagonal or something? Okay, so let's see if we can put this into a sentence. The sum of U and V forms another vector which represents, see if you can finish that sentence. Try to use the word spanned. Okay, so if you include the word spanned here and the word parallelogram here, it would go something like this. The sum of U and V forms another vector which represents the diagonal of the parallelogram spanned by U and V. Spanned by U and V. Okay? If the word spanned confuses you, because it is a new word, just change it to the word implied. Implied by U and V. Because that's kind of what spanned implies. It implies the word implies. Okay? All right. Good job. Okay, that's our first investigation, our first conjecture. And by the way, it's true for all vectors. It doesn't have to be our vector U and our vector V. It can be any two vectors. That's a general takeaway from a specific example. We try not to use inductive reasoning like that in math, like, oh, well, it worked for those vectors, so it must work for all vectors. But sometimes we just play around with stuff to investigate new truths. To be honest, the proof for what I just showed you isn't very complicated. I just don't have time to explain it. Okay, there's another way, though, to think about adding vectors. Not only is it the diagonal of a parallelogram, don't sleep in my class, it is also a shortcut of a journey. Okay, so this next drawing looks very different, but it gives us the exact same result. Okay? Okay, so we're going to start over. This time we're going to draw U and V a little differently. Instead of putting them tail to tail like we did, we're going to draw vector U first. So find the point 8, negative 9. Maybe I should zoom in a little this time. This would be a good time to do it. Okay, so find the point 8, negative 9. Alrighty. Draw your position vector U. Okay, now, instead of drawing vector V with its tail at the origin, we're going to draw vector V with its tail on the head of U. Okay, I'll say that again. I want you to draw vector V starting here. So where U ended, that's where we're going to start drawing V. Does that make sense? Okay, so go ahead and start here at the point 8, negative 9, and draw me a little negative 3, 2 vector. Remember the worksheet last night? You did draw vectors in more than one place, right? So we're drawing V way down here now. Okay, so you're going to go left 3 and up 2, not from the origin, but from the point 8, negative 9. So this is still the vector U, this is still the vector V. Now, you just connected them tail to head. Where did the head of U and where did the head of V end up? What point? 5, negative 7. Interesting. Isn't that the same point that was the opposite of the parallelogram? Opposite corner of the parallelogram? Okay, so you just terminated right at the point 5, negative 7 again. So plot that point. Put the parentheses on there. That's your coordinates, right? Coordinates. Okay, which means if this was like a journey, a path, and we first, let's say you're driving to San Diego, and you're driving down the 5 South, when you pass San Clemente, there aren't many towns after that. It was like some small towns, a lot of surfing places, trestles, and old mans and all that. But you're gonna pass by San Clemente. If you don't get lunch now, you're gonna have to wait a while. So let's say you get all the way down to like Palizada exit, and you're like, man, you know what? I want to In and Out today. So you turn around, and you drive back up to Avery Parkway. Okay, you get off and get your In and Out burger. You hop back up here. Okay. Well, you could have just gone straight to In and Out in the first place instead of turning around like that if you had been more mindful, right? Well, the shortcut journey would have been just to go straight from 0, 0 to 5, negative 7, right? That would be sort of the shorter, faster way to do things. Draw that path. That is the vector 5, negative 7. So we have two ways of thinking about the vector 5, negative 7. We can think of it as the diagonal parallelogram, or we can think of it as a shortcut journey. Okay, shortcut journey. Make sure you put a head on it. If it's a shortcut journey from 0, 0, then obviously the head goes at 5, negative 7. Okay, this is a little bit harder to make into words, but you could say this time that the sum of vectors U and V forms a vector, so this sentence sounds kind of like the last one we wrote, that represents, see if you can finish the sentence. Okay, how would you finish the sentence? The sum of the vectors U and V forms a vector that represents what? What does it represent? A shortcut maybe, right? Okay. So it represents a shortcut of the path formed. Now notice there's no parallelogram in this picture, right? It's more of a pathway thing. And that's because I didn't put U and V tail to tail. I put them tail to head. So I'm going to just put, it's the shortcut of the path formed when U and V are placed. And it's really tail to head, but I don't know why everybody says head to tail. Okay, I guess it makes sense. Vector V is attached, its tail to the head of U. Or you could say that U's head is attached to the tail of vector V to form a little pathway. So see the blue-red path? The shortcut is the green path. Okay. So what's cool about this is we have geometric ways of thinking of addition. Okay, so here's our conjecture, our first major conjecture. The sum of two vectors can be found algebraically by adding the x and y components. No big deal, we did that. U plus V. We did that by taking 8, negative 9, and literally adding onto it negative 3, 2. We got the right answer, so don't get me wrong. You can always do this to get the right answer. It's positive 5, negative 7. But see, that's algebraic addition. What is not obvious is that there's a geometric interpretation of everything in the vector world. So we could also find it geometrically by either one of the following two methods. You can draw the diagonal of the parallelogram, spanned or implied by the original two tail-to-tail vectors, or you can draw the shortcut vector of the path formed by the original two tail-to-tail vectors. The first method is often called the parallelogram method. Parallelogram method. And the second one is often called the head-to-tail method. Okay? Neither is hard to do. I'm just going to take a quick class vote. If you like the first method where we drew the diagonal parallelogram, raise your hand. If you prefer the shortcut path method, raise your hand. Interesting. Because it turns out that most of you voted for the shortcut path method, the head to tail, the second one. Turns out that one's really easy to use when you're adding 5 or 6 or 7 vectors together. The parallelogram thing gets pretty ugly. So you're totally right to vote for that second one. Let's see if you can now add 4 vectors by creating a pathway. Okay? So this is now you try, discuss with your neighbor how you might geometrically add the following 4 vectors and then do it. So first discuss it, then do it. And I'm not talking about just going like this. Okay? I don't want you to just add these up. You can do that to check your answer. But I'm not talking about that. I'm talking about how would you geometrically add them up. So discuss it and then do it. Okay, so you start by drawing vector k. It really means up to. 0, 2 means up to. And then you, from that head, you're going to go left 1, up 3, like that. And then from that head, you're going to go left 3, up 4. And then from that head, you're going to go left 2. Negative 2, 0 means left 2. Try to always make sure your arrowheads terminate, stop, at the point that you're traveling to. Okay? So never make them too long or too short. That's the goofy path of the indecisive driver. Okay? Now we're going to draw one shortcut path as the crow flies. And you can see we clearly end at the point negative 6, 9. So this is the vector negative 6, 9. And what's cool is when you add these up, you get negative 6, 9. So you wouldn't probably do this with a parallelogram, but you can do it with the shortcut method. The head-to-tail method works great for adding multiple vectors together. Okay? All right, good job. Let's go on. There's more to talk about. What would happen if we took vector v and added it to vector v. So obviously, we can add u and v, or k, l, m, and n, but why not add a vector to itself and see what happens? Okay, so remember the vector v is the vector negative 3, comma 2. So this is our second investigation. So vector v is negative 3, 2. We're going to add it to itself. And I mean with a picture. Geometrically add it to itself. Okay, so I kind of just drew it real quick there. If you go left 3 up 2 and then another left 3 up 2, ultimately you just went left 6 and up 4, didn't you? Okay, so if you were going to draw a shortcut journey, that's the vector u plus v. It would just feel like you're tracing both of your original vectors. So the vector u plus v is right on top of, I'm sorry, it should be v plus v, my bad. They're both v, so you just, the vector v plus v is basically right on top of the two reds. So I really wouldn't call that a parallelogram or a triangle. It's just kind of an overlapping thing. But we learned something from it. We learned something. How long is the, or what is the name of this green vector? If you had to give it a bracket component, rectangular component name, what would you call this vector in green? Negative 6, what? 4 is correct. Negative 6, 4. Okay, so it looks like, here's what it looks like to the person investigating. It seems like if you add v plus v, you just get negative 6, 4, right? And we know that this is 2 times negative 3, and this is 2 times 2. So we could pop a 2 out, kind of like we did yesterday. But wait a minute, this is 2v. So it seems like adding v and v can also be written as 2 times v. Now before you say, come on, Mr. Shore, that's obvious. V plus v is 2v. Nobody ever told you that vectors, a multiple or repetitive addition in the world of vectors represents multiplication. Nobody ever said that. We just sort of discovered it. Okay? We're studying a new branch of mathematics where anything is possible. And there might be new rules that apply. Well, it turns out, lucky for us, that just like 5 plus 5 plus 5 is 3 times 5 in the world of numbers, so v plus v plus v is 3v in the world of vectors. So we got lucky with that. Vector addition, when you repeat it like that, can be represented as multiplication. That's good news for us. It means it works very similarly to numbers. Okay, another thing it means is that 2 right there. Do you remember what happens to a function f when you times it by 2? What happens to a graph like this when you put a 2? Like let's say it's a cosine x graph and you slap a 2 in front. What does it do to the graph? Stretches it, right? In the world of vectors, coefficients like this scale or stretch the vector. Okay? So this means we can call the number here a scalar. Has anyone ever heard that word? Maybe your math teacher, your science teacher mentioned it or whatever, a scalar? Like, what the heck's a scalar? Listen, it's just a number, and it's the coefficient. So what it does is it just stretches or shrinks your vector. If it's bigger than 1, it stretches your vector. If it's less than 1, it shrinks your vector. It's a scalar. That's his job. He scales. Okay, so right now we're just going to write down a few little notes. This guy is called a scalar. Scalar. And you can just think of it as a compression or stretch factor. So it basically stretches or shrinks the vector. So vector v has been stretched twice as long. That's what it means. Okay, without doing a lot of detailed sketching, what would 3v look like? So now I want you to think not in terms of stacking vectors, but I want you to think in terms of stretching this vector. If this is v, what does 3v look like? Go and draw it. What would 3 be? Because it says draw v plus v plus v. We've already said that that's going to mean 3v. That's going to mean it feels like stretching the vector v 3 times its length. So go ahead and stretch it 3 times longer. And see if you can predict where it will end. Where will it end? Okay, so it should be 3 times longer. So instead of left 3 and up 2, it's left 9 and up 6, basically. So our green vector would just basically take us to the point negative 9, 6. Okay, so this is why you'll hear the word scalar. It just means number when it's in coefficient form like that. Okay, now, what is conjunction number 2? Multiplying a vector by a what? Scalar, or you could put real number. Multiplying a vector by a scalar or real number is equivalent to scaling the what? What's the fancy word for length? Magnitude, right. It scales the magnitude of the original vector. Interesting. That's just an observation we kind of made. Let me show you a quick demo of that. So Mr. Shore has here the vector negative 3, 2. I did a minute ago. Hold on. Okay, there's the vector negative 3, 2. And I'm going to scale it by a factor of c. Okay, so as I control this, you can see when I change the c value, that's just the constant front. It stretches or shrinks the vector accordingly. By the way, if I can shrink it down really small, so its length is exactly uno, it's then called a unit vector. Remember unit circles? A circle, radius 1? If you take a vector and you shrink it down to size 1, it's called a unit vector. It's a good name for it. We're going to discuss that in the next part of the lesson. But see how I scaled it back and forth like that? Okay, I wonder what would happen if we multiply a vector by a negative. That would be like the next investigation. So let's go back to our work here. Clear the ink. Now where are we at? Okay, remember that geometric interpretations of arithmetic is not really new. Okay? Back in 7th or 8th grade, your teacher might have tried to explain to you that 5 minus 2 is the same as 5 plus negative 2. These really are the same thing. This is so obvious to you now, but when you were young, I'm not sure it was that obvious. So the teachers would use like examples of money. They'd be like, somebody gave you $5, but you owe your friend 2. So how much money do you really get to spend today? Well, 5 minus 2 is 3. So then they tried to introduce the idea that adding a negative means the same thing as subtraction. Okay? So one way they often will do that is to give you a number line, and since everybody kind of starts counting at the 0 mark, imagine just going right 2, 3, 4, 5, and then back 1, 2. You would find yourself at the point 3. Well, guess what you just did? You just did vector addition. Okay? You had a vector, right? And then you went back a vector, and then you found the shortcut journey. See? So you have a vector that goes right 5, and then another vector that goes back 2. That's like a u and a v vector. And then u plus v is that little shortcut journey there in green. Right? Okay, so what does it mean to add geometrically? It means to use a number line and count the spaces back and forth. So you've actually kind of done this before, but it was all one-dimensional. Okay, now let's go to this. How do you think we should define u minus v? Like, if you had to draw a picture of not u plus v, but u minus v, how would you draw that picture? How would you draw the shortcut path picture for u minus v? We've already done u plus v. Okay, so remember, u is the vector 8, negative 9. V is the vector negative 3, 2. I want to see a picture that tells me the difference. Just like a minute ago we had a picture that tells us the sum. Okay, so I'm going to pause it for a second. see if you can think of it as u plus the opposite of v. Let's go over that one real quick. So you're going to draw u. You don't have to draw it at the origin, but you can if you want. 8, negative 9, right? And we're not really adding v to it. We're adding the opposite of v. So what is negative v? If v is negative 3, 2, what is negative v? 3, negative 2 would be correct. It means write 3 down 2. Let's put our phones away. Okay. It means write 3 down 2. So you would go ahead and go from this head, write 3 and down 2, so something like this. And you find yourself right on the corner of my graph paper, and then you draw yourself the green diagonal, or the green, shortcut. Okay? So this would be the vector u plus negative v. In other words, this is the vector u minus v. So we have a way now to subtract vectors. We just think of it as addition of an opposite. You can see also that if you did v minus u, it would have felt different because you would have actually traveled the v direction and then done the opposite of u direction. You would have actually ended up way up here on the left. Okay? So anyway, where did we end up? See, it's getting kind of hard to see it. I think the head of that green arrow is at what point? 11, negative 11, right. In other words, it's in the direction of 315 degrees exactly, right? Okay, so anyway, we're not discussing direction right now, really, but let's go ahead and write the answer. It was the vector negative 3, or negative 11, 11, negative 11, excuse me. 11, negative 11, final answer. Let's confirm it algebraically real quick. Shouldn't be hard. If you're subtracting these two vectors, you can just basically think of it as adding negative v. And Mr. Short already changed the signs on v here. So what you see here is negative v. I meant to do u is 8, negative 9. Sorry about that. And then we're adding the vector 3, negative 2. So this comes out to 11, negative 11. So that's vector u plus negative v, or u minus v. Okay, so how would you describe it? You would create a pathway where the second vector has what? Been reversed, right? So you're going to reverse the second vector and add it to the first. So how about reverse the second vector? Reverse the second vector's direction and add it to the first. So reverse v's direction and add it to the first vector u. So fortunately for us, the geometry part of it isn't that obvious, but the arithmetic is always a great backup. Like, you just want to add them algebraically real quick. You can always get your answers, and then you can make your pictures work. Okay? The pictures are an important part of this lesson. I'm not going to say the pictures are less, like a worse way to do it. I think the geometric addition is just as important as the algebraic additions myself. Okay? So that's why I'm emphasizing it. Okay, and what do you think negative v even means? Because v was the vector negative 3, 2, and you guys said the negative v vector was 3, negative 2. What do you notice about these? When you draw them both, right? When you draw v, it looks like this. When you draw negative v, it looks like this. If you had to compare v to negative v, what would be a great way to describe them? Do they have anything in common? Do they have anything that's different? That kind of thing. How would you describe a negative v? Okay, so we could say it is equal and opposite to vector v. So it is equal. By that I mean same in magnitude. Yet opposite. By that I mean 180 degrees difference in direction. 180 degree difference in direction. Okay, so we already kind of learned a lot today. This next part is actually, it's really easy, but I think I want to save it for tomorrow. I kind of mentioned that if you take a vector and you kind of shrink it down to size uno, we call it a unit vector. So that's one of our big goals tomorrow. And we'll also talk about dot products.